Hey guys, what's going on? Welcome back to Your Forest Podcast for those of you that are returning, and welcome for the first time for those of you this is your first time. I'm Matthew Christoph, and today I've got a intriguing podcast for you guys about forest genetics. It's not a topic I know anything about whatsoever. Unfortunately, when I was in school, the program didn't really exist. Now it exists, and it's super interesting. We talked a lot about monocrops, and we talked about grafting, and we talked about resilient forests, creating forests that are resilient to drought from climate change. We talked about creating trees that are resilient to pests and pathogens, all kinds of different interesting things. There was a lot of, I think in the middle of the podcast, we started spouting out a lot of Latin names. So Populus tremuloides and balsamifera and stuff like that. Those are just Latin names for tree species. So if you don't know what those are, you can just Google exactly that. It'll pop up. You'll know exactly what tree we're talking about. All those we were talking about were all deciduous species. They all look kind of the same. Yeah, it was a super interesting podcast. I know nothing about it. There's a lot of confusion around genetics when it comes to the forest industry, and people get concerned that we're going to create these this term that was coined, Frankenforests, create these forests that are all GMOs, and they're not natural, and they don't allow for biodiversity, and they're monocrops, and that's not what's going on. So I brought Barb Thomas on. Barb Thomas is a bunch of stuff. She's associate professor at the University of Alberta. She's also the industrial research chair for a tree improvement program, helping improving tree genetics and tree improvement in Alberta. Yeah, she's at the University of Alberta. She teaches courses there. Yeah, she's a very knowledgeable woman. She had over almost 2 decades as an industrial scientist. Yeah, she came in to talk about everything that they're doing and to address some of my misunderstanding about genetics. And trust me, there's a lot of it. Yeah, so as far as sponsors for today, we have Green Lake Forestry, as always. We also have Forest Resource Improvement Association of Alberta, so FRIA. She mentions FRIA actually in this conversation a little bit, so that you guys know what that is. Also, Damaged Timber is also a sponsor of the podcast. They are an apparel company, and they are creating a scholarship program for students in environmental sciences. 10% of the sales of all their clothing goes back towards this scholarship program. So if you guys want to support something that you agree with, support something that you want to support besides just buying clothes, everyone's buying clothes anyways, you may as well support something you believe in. That was a really long-winded way of saying that, but I apologize. If you go onto his website, damagedtimber.com, you put in Your Forest 10 at the checkout, and you get 10% off everything. Without any further ado, we will jump right into this podcast about forest genetics, Frankenforests. Here we go. When I think forest genetics and that kind of stuff, it's not something, like I was telling you earlier, I don't have any kind of education in it whatsoever besides basic genetic principles. I think people immediately the public especially, they get a little bit freaked out, and they think, oh, you're messing with the genetics of the forest, the biodiversity, or you're going to create a monocrop that's going to take over and be more productive and kind of become an invasive species. Right? I think people that aren't in the know, that's kind of where their mind goes. And I just wanted to get your take on what we're doing out there. Are we we're not planting non-native species. We're not.
So our forests in Alberta, in particular, are all on Crown land.
Right.
And so that is all governed by regulation by the government. Mm-hmm. And there are many, many different objectives that are trying to be met in our forests. And one of them, of course, in our productive land base is fiber.
Right.
And that fiber goes to mills for all sorts of processes, supports communities, etc.
That's where the money comes from to do this research. So
That's right. That's where a lot of the money comes from to do the research. And the Canadian public in general through some of the grants, for sure. So those regulations help us guide decisions around diversity and to ensure that our forests will be there in perpetuity, even within the context of tree improvement. And selecting on traits that are specifically geared towards increasing fiber production, for example. So that is for sure one of the main objectives in tree improvement.
Of course.
And that's okay.
Yeah.
Because we also have a shrinking land base here. There are many, many demands on our land. And a lot of our productive forest land is being taken out of productivity from expansion of oil and gas, infrastructure, roads, all kinds of things, you name it, mining.
Mm-hmm.
And so that becomes a challenge, how to...
Even urban sprawl.
Yeah,
right? Like,
urban sprawl,
Yeah.
for sure,
Yeah.
for sure. So the species that we work with are all native.
Right.
You're not allowed to plant non-native species, although some of the indications around climate change would suggest that we'd be better off to consider some species that are more tolerant of drought, for example, and start to test those in our areas on a small scale to see whether or not they're adapted and can withstand not just the drying trend or the warming trend, but the extremes, because the extremes are what are really hammering our forests.
Yeah.
And then having other subsequent effects, such as mountain pine beetle. A lot of the mountain pine beetle infestation has been driven by climate change and not having cold enough winters to kill the little devils when they're, in November. It has to be at a specific time, and it has to be super cold, and it has to be that cold for like 3 weeks.
Is that how long it is? Okay, I thought it was just like they needed like minus 35 for like 4 or 5 days or something. But it's a while for the cold to penetrate and kill the larvae.
Yeah, I'm not an entomologist.
No, obviously.
And so I wouldn't want to be quoted on the 3 weeks, but I understand it's significantly longer than just a quick cold snap.
Gotcha.
For sure. And it also has to occur at the right time of year. If it happens in January, February, I believe it's too late to really have much impact.
Okay, I'm having a deer on in a couple of weeks, so he can speak to that.
Oh, okay.
Yeah,
I'm sure he will.
Yeah.
So, what we're trying to do is we go out into the forest and we identify trees that look, let's call it, superior to their neighbor.
Okay.
So that means a tree that is a bit taller, maybe a bit straighter, shows no sign of disease, cankers, things like that on the stem. And we identify a large number of these individuals in a particular region.
Okay.
We collect seed from them. We collect a little piece of wood tissue from them. It's called scion wood.
Okay.
And then we are able to take that seed, grow the seedlings from it, and plant it out to multiple test sites within a particular area that you're targeting for reforestation with that particular species and group of parents.
Right.
So you could have 400, 500 parents that you've selected from.
Okay.
And then you test those seed, and they're all what we call half sibs. So you collect the seed off the mum tree, and you don't know who dad is.
Yeah.
So dad could be anybody. So those are half sibs. You can think about whether or not, you come from a family where your mom or dad has been married a couple times or whatever and had kids from each marriage.
Right.
Those kids are all half sibs. So
perfect.
Those are so we assume they're all half sibs.
Okay. Yeah, that makes sense.
And then if we have an area that we've selected that we want to plant back to, we have to test those and see whether or not they're adapted, because you might be stretching the boundaries a little bit from our specific seed zones, which guide all regular reforestation with wild seed in this province, and also for shrubs. Right.
So you can't take seeds from, the northwestern part of the province and put it down by like the bottom south piece, right? Like there's specific, these genetics have to stay in their area that they're modified for, or that they're evolved for, I suppose.
Yeah, that they've evolved in. And this concept that local is best is kind of a premise.
Makes sense.
Within that, though, there are still individuals that are faster growing, have higher wood density, have a whole variety of traits and characteristics that are desirable for forestry that in no way take away from their adaptability.
Right.
Because they are local and native.
Right.
But, there's a range in the population out there.
Right.
And there's an enormous amount of genetic diversity within even an individual tree. So we capture a huge amount with each individual that represents that population as a total.
Yeah, that's interesting. I was curious about that, about how much genetic spread is going on out there. Because I mean, how far like a seed can travel to be germinated and stuff like that. I always wondered how much really exchange of genes is going on amongst genes, but it is a lot.
It's huge.
Yeah,
it's huge. The pollen goes
so far
a long way.
Especially for like deciduous trees, I imagine. Yeah.
Yeah, and I mean, an aspen seed goes a heck of a long way. The conifer seed isn't flying as far, but aspen is, and pollen is just moving enormous distances.
Really?
For sure.
Interesting.
Yeah.
Okay. So yeah, you're getting all kinds of crazy biodiversity, and you're taking local trees and just the genetically superior stock based from the natural conditions, and selecting those and breeding for those to become growing stock in cup blocks.
So we do a couple things. So we have to test them.
Right.
So we have test sites. A minimum of 3 test sites are required on any given area that you want to be working within.
Mm-hmm.
And those are called, in our province, we call them controlled parentage programs.
Okay.
As opposed to a breeding program, which would be a more typical name in another place. But some of our programs are clonal. So there's, which means we take cuttings of individuals as opposed to actual breeding.
Okay.
So everything's called a controlled parentage program, or a CPP.
Okay.
And those CPPs have guidelines as to how many parents have to be contributing to a seed lot that's used for reforestation.
Okay.
So we take those seeds off those original wild parent trees that we select from. We put them out to these, let's call it 3 test sites. Mm-hmm. And we want to test the range of environments within there to make sure that we're no longer just testing in that core forestry area. We're actually starting to expand that testing into more extreme sites, higher elevation, maybe drier sites, to test for those the capacity to deal with that climate change that's coming and is actually here already.
Yeah. No, of course. Yeah.
Our wild seed, the collection requirements for that is you have to collect from a minimum of 30 parents.
Okay. So
they're very strong regs and rules around genetic diversity to make sure that we will have, as I said, sustainable forests into the future. Mm-hmm. Then remember that little piece of wood I told you we take the cutting of?
Right.
Those little pieces of scion wood, it's just like horticulture or with apple breeding or apple trees or whatever.
Right.
You graft that piece of wood onto a seedling.
Oh, okay.
So that you have exactly the same genetics of the parent tree grafted onto a seedling as a rootstock.
Oh, okay. Because
you can't root the piece of wood.
Right. And can you explain the grafting just a little bit more? So, what the purpose is there and how exactly that works, just so people can get a picture in their mind.
Yeah. So seedlings are grown for 1 to 2 years as you start this process of going out to the wild and collecting those parent trees. At the same time, you're growing seedlings in a greenhouse. And they will have come from a wild seed lot from that area, so they're adapted as well.
Right.
And what we want to do is we want to have multiple copies of that individual parent. Mm-hmm. So the only way to do that is to take multiple cuttings off that parent, and then we cut the seedling along the cambial region.
Right.
And then we cut that little piece of wood also so its little cambial region is showing.
Okay.
We stick them together.
Right.
And tape it up, basically.
Okay.
And then they basically form a single tree out of that.
Okay, so
they grow together.
Okay, and that'll change the seedling's genetics slightly?
So we don't really care about the seedling part. We just want that to be a rootstock.
Okay. Oh, okay. I see. Yeah.
Yeah, and so then we take all those grafts. So let's say we graft 10 of each of our parent trees. Mm-hmm. Then we go to a piece of land that's been prepared and is fenced, and we're going to build what's called a seed orchard.
Okay.
And we're going to distribute those 400 parents across that seed orchard in a pattern that will minimize the amount of crossing between the same tree.
Okay.
Because we don't want inbreeding. Inbreeding is bad.
Right.
Inbreeding.
That's a good rule for life in general.
Yes, it's a very good rule. And trees do not do well when they're inbred because they have so much diversity that when you start to inbreed them, all kinds of crazy things show up that turn into really nice ornamentals.
Yeah, as they do when cousins are made. Yeah.
Some of those, So we have this orchard that starts to grow. At the same time, we have seedlings growing about those parent trees that we now have in this orchard.
Okay.
So then we need a bit of time. And this is one of our biggest challenges here in Alberta is now we sit and wait basically for 10 years, 15 years, sometimes 20 years.
Wow.
2 things happen. Yeah. One is the seedlings out in those test sites are growing, and so we get a good idea of their performance and their relative performance to each other.
Okay.
Because on those test sites, we have what's basically a common garden. We've controlled the environment, so we're now allowing for the genetic expression and the differences between those different families. Mm-hmm. So we call those single tree collections a family.
Okay.
And we can see whether, in fact, what we thought was a good tree in the wild actually turns out to be a good tree when all other factors are controlled.
Right.
So there's no competition.
Yeah.
They might be watered, whatever.
Right. It wasn't an accidental perfect microsite or something when it germinated or
Right. And a moose went by and fertilized it.
Yeah.
Or some other thing like that happened, right? And
right.
we don't know. We'd have no idea because what we see in the wild and what everything is a phenotype.
Mm-hmm.
So just that physical, characteristics you see.
Right.
But they're components that phenotype are derived from.
Mm-hmm.
There's a genetic component.
Yeah.
There's an environmental component. And there's the interaction between that genetic and environmental component.
Right. So you're taking all that away, so it's just the genetic component.
Yeah, right? You're trying to control or minimize that environmental component as much as possible.
That makes sense. Yeah.
And the G by E, or the genotype by environment interaction part, we try and get at by having those multiple test sites.
Right. So how close in proximity are these multiple test sites? They have to be a certain distance away from one another, different elevations? They
need to represent the region that you want to plant back to.
Okay, yep.
The deployment area, so that you have captured well that environmental gradient that's within an area, a zone that you've worked hard to figure out is a good zone to begin with, but now you have to actually test it.
So would you... So let's say there's a seed zone. Are seed zones based off of natural subregions, more or less?
Yeah, and then they go down from there, and there's a whole series of characteristics that they've been refined around.
Okay, so one seed zone wouldn't go across like 2 or 3 different natural subregions. It would generally be based in one subregion, so you just want the variation within that subregion.
So as I mentioned, with the tree improvement, and because of the testing, we can make one of these CPP regions bigger than a seed zone.
Oh, okay. Right. Oh, yes.
So you might have half a dozen seed zones that are captured within one region, which makes it much easier for forest management,
right? For
planning, because if you're harvesting in multiple areas and you need to replant in those multiple areas, if you have one single set of parents you can go to and know are well adapted, that gives you a lot more flexibility in your planning.
Gotcha.
So at the same time, back in our orchard, those trees are growing now.
Right.
And maybe around, depending on the species, maybe around year 8 or 10, they start to flower.
Yeah.
Well, they start to develop conelets.
Conelets?
Yeah, they don't really flower.
Yeah.
and those conelets, turn into cones.
Right.
And so, and those produce seed. And so at the same time, you're starting to get information.
Right.
That tells you about those parents from their progeny growing in the field. Plus, you're starting to be able to harvest a crop.
Gotcha.
Off that orchard.
Right.
So we do 2 things with that information from those field test sites, those progeny trials. One is we can go back and make inferences about mom from the parents and decide that's really not the mom we're looking for. When tested on a common garden site, the progeny are not very big. They don't have very nice form. They might not have a nice branching characteristics, whatever our traits are that we're picking.
Right.
They might not be disease resistant.
Right.
We take that mom out of the orchard. That's called roguing.
Okay.
It's a great word. You go in and you rogue your orchard.
Yeah, it is a good word.
So we use that to do that. Then we also figure out who the best individuals are in those progeny trials.
Okay.
And this is called forward selection. The last one's called backward selection.
Okay.
So as forward selection, we pick those best individuals and we can breed those manually ourselves and do a controlled cross.
Okay. Yep.
And we can take those progeny and start to test them.
Right.
At the same time, we can take our scion wood from those individuals in the progeny trial and build a new orchard.
Okay.
And so every time we do this step, we're incrementally changing the mean height, for example, or the volume in the population of trees that are supplying the seed for reforestation.
Okay.
So that's what is helping us grow our forest a little faster on an ever-shrinking land base.
Right.
So that we try and maintain the same amount of fiber, if not increase our fiber supply a little bit.
Right.
On the land base available to do commercial operational forestry.
Right, while maintaining genetic biodiversity and making sure that as normal evolution would occur, that the genetically superior stock is continuing. Yeah, that makes sense.
Yeah, and there's ingress too, right? Seed will come in to a reforestation site from outside trees, so that's adding to the diversity as well.
And it may be there already too after a cut block. There's tons of, in the seed bed, there's already going to be plenty of seeds in there that'll probably take off, especially aspen, right? Like, yeah.
You want to control some of, there is some control. You have to meet some growth and survival
Of course.
criteria, right?
Right.
And so you do want to also give those best individuals, those best seed lots that you put out there, a chance to actually grow well.
Yeah.
So you will probably do some kind of silviculture out there.
Mm-hmm.
But the other thing to keep in mind is for any company or government program that is in tree improvement, there is also a conservation program that goes in parallel.
Oh, okay.
That requires areas to be set aside in terms of natural reforestation going on in those areas, for example. So if you there's a series of criteria to meet the requirements for conservation, but for example, you could go in and harvest there, but you have to collect seed from that stand and put that seed back out.
Regardless of whatever's going on genetically. Okay.
Yeah. So you are maintaining areas of wild seed no matter what.
Right.
No matter how quickly we increase in terms of the deployment of the improved seed.
Right. So is that, in those situations, it's, we call it left for natural, right? That's what we're talking about. So you could go in and do a little bit of mechanical seedbed prep or something, and then allow it to take over on its own type thing.
Or if you're going to harvest, though, you'd have to collect seed off those trees.
Okay.
And then put them back out there, or grow seedlings and plant them back.
Gotcha. Okay.
So forestry isn't completely restricted in those areas. Like, they're not complete reserves by any means, but you have to be careful how you manage it.
Right. Yeah, that makes sense.
Which is good. So.
Yeah, and I think that clarifies a lot. I think people, it's just funny. People go straight to the kind of Orwellian view of things, right? And they think like, we're genetically modifying everything and it's going to be a monocrop and everything's for productivity and not for whatever, right? So I think it's good that we get through that and explain that there's other factors being considered here. So perfect. Yeah, I guess that got through like a bunch of the questions I had for you, actually. So reading through your website you have from the U of A there, you guys were talking about creating genetically superior stock in relation to resilient forests. So resilient towards drought-caused climate change, resilient towards pests, resilient towards those sort of things. How does one go about selecting for those specific trees? How do you know what I mean? How does that work? I'm totally in the dark on this. I don't know how you figure out like which ones are good with drought and which one is it just more testing the same way, more of the progeny sites and all that, or? Yeah.
So what we're doing with the Res4 Resilient Forest Project is taking two existing tree improvement programs in the province, one spruce and one pine, and we're working exactly with those original parents that are in those programs now. Okay. Each of those programs is at a point where they're moving from what's called the first generation to the second generation orchard. Okay. So we have a chance in this project to help guide those selection decisions. Mm-hmm. You remember I mentioned we have to sit back and wait for things to grow for, 10, 20 years.
Yeah, it takes a long time. Yeah.
It takes a time.
It's a slow process.
So what this project is about is now using the genetic sequence of the trees, of the progeny that are out in those progeny trials, and linking that with models to the phenotype that we measure. Okay. So the height, diameter, wood density is an important trait, microfibril angles, characteristics such as that. Right. There are traditional ways of calculating a breeding value, which tells you about that parent and whether you're going to decide to rogue it out of the orchard. Mm-hmm. And those methods rely on this long testing time.
Takes time, yeah.
Yeah. So there's a model that gets developed to a breeding value that's based on a model. So what we're trying to do now is speed up the process of being able to make that decision. So we have a training population from those progeny trials that's going to train our models. Okay. And then we're going to verify those models with a smaller population, a subset. And that is where we're really getting at the crux of trying to identify which parents within our existing programs have the range of variability that will give us that drought tolerance. Okay. So we're doing an experiment this spring right now. We're setting up for it right now, where we have a selected number of parents out of that program and original seedlings from those 30. Now, these trees are 35 years old in those progeny trials we're working in.
Yep.
And we have seed from those original parents that we've regrown this year, pine and spruce. And we're putting them in a greenhouse trial, and we're going to do a drought experiment on them.
Gotcha.
So we're going to have some that are well watered and some that are dried down, re-wet, dried down, re-wet, dried down.
Lots of stress.
And lots of stress. And we're measuring a whole bunch of characteristics.
Cool.
Physiological characteristics, chemical ecology, metabolomics, all kinds of crazy things are going to be measured on these trees. It's quite exciting. Plus, they'll all be genotyped. So their gene sequence will be identified through a technology called genotyping by sequencing.
Okay.
And that's being done at Cornell. And all those original progeny in the trials, in the bigger trials in the field, have all been gene sequenced as well.
Okay. Interesting. So when you said something about training, you said they're training.
So we need to have those older trials to actually build solid models that link the phenotype with the gene. So we can figure out which genes, gene sequences link to a particular phenotype.
I see. Okay.
And so the idea there is that for the second generation, we can in essence skip that long progeny testing phase.
Right.
But by just genotyping an individual, we can then run the model with our genomic estimated breeding values now, instead of our pedigree-based breeding values. We can take the sequence, run our model, and make a projection of which are the best individuals to go onto the land base and to be the parents. So we are able for at least one and possibly two generations, depending on how robust these models are, skip that testing phase.
Okay. That speeds things up.
It would speed things up because we are in a time crunch here. Our rotations are extremely long. Our testing phases are extremely long.
Yeah.
So we still have to do the breeding. There's three components. There's the breeding, the testing, and then the production.
Yeah, so you're looking at...
So we're shortening that testing component. Yeah. There are ways to shorten the breeding part on the front end and also the production on the back end, but we're not tackling that in this project.
Gotcha.
But what we're trying to do is piggyback a number of key traits here. So drought, and then mountain pine beetle resistance.
How do you test for that in a controlled environment? I guess you just literally just let mountain pine beetle go in the greenhouse.
Not in that case, no. So pine beetle like mature trees.
Yeah.
They don't like seedlings.
Right.
So we're actually going to use one of the funguses that they carry.
Oh, okay.
Fungi.
Right.
That they carry, and we're going to inject that into the seedlings.
Okay.
And again, Nadir will tell you more details about that process. But his part of the project, because he's a co-PI with me on this project. So this is a project I lead, but I have two co-PIs. One is Yusri Al-Kasabi at UBC, and he's leading up the genomics side of the work, and Nadir Erbilgan, who's doing the entomology side. Okay. And then there are actually a total of 25 of us.
Gotcha. So, it's a big project,
There's a whole social science component to this project as well.
Of course.
Which is really, really important to the delivery of our results and our technology.
Yeah, you got to try not to scare the public. Yeah.
and just to fully disclose how this process works and why I come from not from the genomics world.
Okay.
I come from a more classical breeding background.
Gotcha. And
actually from horticulture originally and then into forestry.
Gotcha.
And I've never been a huge, gel jock, let's call it. But I've seen it. This is a massive change in the technology with these new sequencing methods.
Right.
And I see a real opportunity for us to help our programs jump forward at a really critical time in this province because we are faced with huge challenges with our climate.
Yeah, it's changing relatively quickly, right? Like
it has changed.
Yeah, it has. Yeah, exactly.
It has changed. It's documented change in the last 15, 20 years. It's incredible.
Yeah, it's undeniable at this point. Yeah, it's pretty fascinating for me to run into people who I understand they have values that are being questioned regarding climate change, but it's like you have to take science word for it. Like I think a lot of people will go off on, well, there's this scientist who says that, it's not human caused or whatever, right? And it's like, well, 99.9% of them think that it is. So like, I would go with the majority on this one.
Yeah, and I think the thing that's super confusing about it is that it's not just that mean temperature change,
right,
or mean dry down. It's these extremes.
Yeah.
And so if you have a particularly cold bout or a particularly warm bout or a really rainy period,
yeah,
it's hard to believe that on average things are changing.
Mm-hmm.
Because you are subjected to the weather of the day, and you're like, holy smokes, it's wet out there.
Yeah, my favorite was I think it was a congressman or something in the States who brought the snowball in it was like in May or something into Congress and put it on the table. He was like, climate change, hey? Why is there snow on? Like, it's like, you guys, come on, guys. Like, weather, climate, different things. Like, let's get this basic understanding under wraps. Yeah, it's interesting to me how to. I'm still trying to wrap my head around, like how we can predict where to plant these different stocks. So say you figured out what kind of spruce or pine stock is genetically superior in relation to drought resistance because of climate change. So how do we begin to move seed zones and stuff like that to be related to climate change, right? Because we predict where these seed zones are going to move maybe, but how do we get around the legality of it, and as well as how do we know for sure that we're not going to cause a different change that we don't mean to cause, right? It's a crazy subject.
So there is an organization here in the province called Tree Improvement Alberta,
right?
And through that organization, we've done a number of research projects. One of the ones underway right now is funded through FRIA.
Okay.
I'll let you explain that acronym.
Yeah.
and it's to continue on work that was already started to test climate extremes for a number of our key commercial species. So there's a series of test sites right now that are being developed that are way in the south of the province, way in the north, higher elevation, extremes from our typical planting areas.
Okay.
And the purpose of those trials is to test populations of spruce and pine and under less, normal, classical, core reforestation areas, and see how they do in general into being moved large distances. So we've got a very select group of populations that are being picked in by the government and in conjunction with industry, and we're going to try and test some of those boundaries because that's how we're learning about that seed transfer.
Right.
There are regulations. There is allowance for seed transfer between zones within the regulations, and you're only allowed to move seed up in elevation. You're not allowed to move seed down in elevation. You're allowed to go from one seed zone to another. Some of that's just because maybe a company can't manage to get a crop of the species they need in another seed zone, like spruce only has mast years or high production cone years every, 6 to 8 years or something.
Yeah.
So you don't always have what you need in the seed bunker.
Right. So is the only moving up in elevation, is that in relation to climate change? It is.
Yeah.
Okay. Yeah.
BC has taken an extremely aggressive approach to this, and they are actually going to move away from the whole concept of seed zones and do their deployment based on climate.
So did they have, obviously they must have been doing studies to back this up.
Yeah, they've got a whole series of test sites out there where they have different combinations of seed lots that are, they're blended from different populations. And I don't know the exact details to explain it well enough here.
That's okay.
But it's been quite sophisticated. They've had a whole range of species out on these test sites, and they've, put a lot of funds into developing a model which will allow, so if a company is cutting in an area and they need to reforest in that area, they can punch that into their database and figure out what is the best suited seed lots to go back there.
Right. Okay.
Pending future change.
Yeah. It's interesting.
So we're not at that stage yet here.
Right. We're still.
Sure.
So they must have started these trials quite a while back.
Yeah, some time ago.
Yeah.
And they have an enormous amount of investment in tree improvement in BC that far outstrips what's being invested here. It's an area that, we're a poor second cousin to agriculture in terms of funding.
There is to improve, right? Yeah.
And it's unfortunate because it is our our best opportunity going forward to ensure we do have resilient, healthy forests and supporting our communities in the future is my feeling here in Alberta, for sure.
Big time. Do you think this is kind of outside genetics a little bit, I guess, but people are theorizing that like kind of the aspen parkland is going to start to move northward and take over some of the boreal, and you start seeing more deciduous species than you would coniferous species. Do you think that is, I mean, obviously there's all kinds of questions like rotation time. It takes time for things to happen and for them to move and all that kind of stuff. But are we seeing stressors on these trees, like let's say in the last 10 or 15 years that we weren't seeing before that, like in relation to climate change? Or is that visible? We know that for certain.
Yes, I believe so. And also the aspen is being hammered.
It is too.
It's also getting into trouble. It can't only take so much of the stress.
Yeah.
And it's the repeated drought in the fall, so that when winter comes, the roots aren't protected because the ground's totally dry, and things like that start to wear them down over multiple years,
right?
As well.
So I guess the misunderstanding people might have is that they think, oh well, climate's changing by a couple degrees or whatever, like that the trees should be fine. But it's not the fact that the average temperature is changing by a couple degrees. It's the fact that the extremes are becoming more extreme. That's what's causing the dieback and the change in ecology.
Well, the projections on temperature are pretty robust.
Right.
The projections on drought or rain patterns is not nearly as robust.
Okay.
However, as temperature goes up, regardless, it will get drier.
Yeah.
Even if there's more water.
More evaporation, more
transpiration. And so that demand is there.
Yeah.
And trees can only take so much of it. They have to have more water available than the water they need to photosynthesize and grow.
Right, of course.
And as that balance, if you're at that tipping point, they start to get into trouble, especially if it happens for multiple years in a row.
That makes sense, yeah.
Like one of the things about climate change too is there'll be projections of a region changing, for example. Yeah. And maybe you'll hear, oh, this will be better suited for aspen in the. So yes, okay, but there are existing trees there now. So they're not going to suddenly disappear and be replaced by aspen. They have
it went up a degree, we'll all die off, let the aspen come in.
Yeah, they're all going to walk away and get out of the way and let the aspen come in. You know, so yes, if the ground were bare, you were starting from scratch, sure, you might move aspen in there or some other species, or
it's going to take
ponderosa pine or, some other conifer even.
Right. And that was kind of always my thinking, was that it's, the climate is changing to a point where, these things are moving up. These zones are moving up in elevation, and they're becoming more drought and drier and stuff like that. But like you said, rotation times are long, so it takes a while for the forest to react to that change in climate. And if the climate's constantly changing, right, then it seems like it's going to have a hard time catching up and finding a niche where it is going to be good, right? So it's just it's an interesting conversation to have, and it's interesting to know that BC is going so proactive with that change. I wonder if we'll see the same change soon here. So,
yeah, I'm not sure we'll see it soon.
Yeah, well, hopefully there'll be more input and more research done, and kind of start talking about it a little bit more soon here. Just a fascinating subject, the whole climate change thing. Like on top of that, you look at. It's not just drought, but I've had several people on talk about wildfire in relation to climate change and the increase in wildfire occurrence on top of drought, on top of all these things. Like we might be seeing, a total transformation of the boreal into something different. It's going to be interesting for sure.
The rate of all these changes is what the challenge is. I mean, trees have been subjected. Trees that are living, on the coast, some of them are 3,000-4,000 years old. They've survived an incredibly long time. Yeah. And trees here that can be over 100 years old. Mm-hmm. It's the rate of change. It's so fast. Yeah. Relative to change in climate in the past. Right. That to move seed, naturally. So, this whole notion of, I'm sure you've heard this term, assisted migration. Right. It's not the kind of research specifically that I do, but it's that concept of shifting material faster than it can go on its own. Right. To try and help it out and allow it to propagate and still exist in the landscape. Maybe not the exact same spot, but it'll still exist. So, it's a fascinating subject, and one that I'm sure comes with a lot of speculation and a lot of
just people are unsure, I'm sure, right? Like, people don't want to do the wrong thing. They don't want to take the wrong step. But at some point, someone needs to commit, and we need to try something, right? Because,
we need to, we can just stand still and do nothing and wait and see. Or we can try and build something into our system that gives us some buffer going forward.
Be proactive.
Yeah. And, our Resilient Forest Project we are still working with our native species, with our native parents, and we're just seeing which ones are better suited and that we can try and tailor that crop a little bit to hedge our bets going to the future.
Yep.
Because the other challenge is that as the climate changes, it's going to probably continue to change more into the future. Planting a seedling today is going to need to be able to deal with climate that is different in 50 years, in 80 years.
Exactly.
And how a seedling behaves and deals with stress can be quite different than how an mature tree can deal and handle stress.
Yeah, it's unfathomable to really think about, because like you said, right? Like, sure, we're changing it. We're going to move these seed zones over or whatever so that we'll be hedging our bets, and they'll be good for 20 or 30 years. But then as the climate continues to change and increase in average temperature, then maybe, like you said, in 100 years time, it'll need to be shifted again or whatever, right? Like, it's just it's an ongoing process, it seems like. And fascinating.
It is.
It's a huge problem, and hopefully we can, I guess with conversations like this, people start to think about it, and hopefully it'll stir up some. Yeah.
We're the canary in the coal mine in terms of climate change in this province. If you dig into the literature a bit on this, we are a test case location just because of what is going on here. Our extremes are greater. Our changes across the province are greater.
Yeah.
It's just somehow where we are with the boreal and the plains and the mountains.
It's just the perfect transition zone.
We're like a perfect storm going on right here, right in Alberta. If you look at those patterns of climate that have occurred already over the last 20 years, it's a fantastic testing ground for all this.
Yeah, well, I guess that's beneficial. Someone's got to do it. Yeah. I was thinking about last night when I was kind of going over questions for this. I was thinking about red belt. So the idea that there's an El Nino year or something like that during the middle of January, and the air warms up to a point where the spruce or the pine wakens up and tries to start growing again, but the ground is still frozen, it can't get water, and it creates a die-off. Would that be similar? Could you and do any kind of genetic work to select for that kind of resistance as well in certain areas that are prone to getting red belt kill off? Or would that be similar to drought, or is that just something you never really looked into?
I've not looked into it, but it would just take a bit of thinking about how to design an experiment to test that. Again, you'd probably be restricted to testing it on seedlings, but you could certainly take seedlings out of cold storage, keep their roots frozen, and subject them to a whole series of different, conditions that their needles would be exposed to, whether it's, wind or temperature. Or
wind
whatever.
was another one. Wind was another one that I thought
Hail is also a big one.
Hail, yeah.
So stress resistance has become a much bigger concept than just drought, really.
Yeah. I suppose, like, what would you do for increased windstorm activity? Like, say you had a specific area that was really had lots of wind problems. What would you do for that? Just create a more hardy root system, or more elastic trunk, or how would you do that?
There has been some work done on wind and the impact of wind on trees. I think Vic Liefers did some a number of years ago.
Right.
So for sure, root firmness.
Yeah.
Which could also be linked to the kind of soils you're growing on. So, and maybe certain species wouldn't be very good species to put back into some areas because they are highly, prone to high winds or something like that, or changing wind conditions.
Right.
Branch angle could be an important feature as well in terms of capturing that wind or not. You know how, like, trees up in the mountains, they're shaped so that they shed the snow.
Yeah.
So
all the branches are on one side or something.
They don't really lie flat.
Yeah.
And catch all that snow. They're quite columnar in a way. They sort of aim upwards a bit more. Or the tighter angle.
Yes. Not as vigorous. Not as okay.
Yeah, it's got a different shape, a different form.
Yeah.
And so maybe there are some characteristics that make a tree less prone to being blown over, and you could identify those and select for them. And because the key thing about a trait that you select on is it has to be heritable. You have to be able to, that genetics has to move from mom to the kids, basically. And with most of the traits that we work with in tree improvement in forestry, they're called quantitative traits. So many, many, many genes contribute to that particular phenotype that you see. Right. And so that's why changing things is often quite slow, because there's many genes involved and it has to be heritable.
Right. So it's not necessarily that, for example, you want to select for blue eyes and the kids turn out with brown eyes and you're like, oh shit, what happened? Like it's not, you know what I mean? It's not something
I think we would know what happened there, but
but it's interesting.
But it's not a single gene.
Right.
That resistance for disease is sometimes there's some diseases that have one or two genes that play a role in it. Right. So they either are resistant or they're susceptible. Yeah. It's risky because once the disease overcomes that, everybody's susceptible. Right. But these other traits that we've been talking about, there's lots of variation in them, and they aren't typically linked to fitness, which means they don't usually affect the reproductive success of an individual. So there's lots of variation there, and it hasn't been weeded out down to just a few types of phenotypes that are preferred. Okay. And so there's lots of variation, and you can select on it, but it's a fairly slow process. And how slow that is depends on one major factor, which is how heritable it is. Gotcha. So your heritability is 0, then the environment is playing a huge role in your phenotype, all of it. If your heritability is 1, which is, that value goes between 0 and 1, then it's 100% heritable. Okay. That is the trait that will be passed on to the progeny.
And you guys know which traits are heritable and not, I'm guessing.
So that's one of those genetic features that we could calculate out of those progeny trials that we talked about.
Okay. So that's part of that. Okay.
That's part of that, is getting an estimate of the heritability for the traits of interest. And that's all part of that formula. Okay. But typically, things like height are around 0.3. Okay. 0.4. Wood density can be a little bit higher. And so that's a really important factor in all of this. When you have to breed for going from parent to offspring.
Yeah, that's my phone. Don't worry about it.
I heard something buzzing.
I got it on to vibrate, but I think I got to find a more muffled spot to put it.
So I can't remember your question anymore, but
I don't know either. Damn phones ruin everything. Another thing I wanted to discuss that I don't know anything about is hybrid poplars. Do you do any work with that?
I have done quite a bit of work with hybrid poplars in the past. Yeah. Okay.
So hybrid poplars, for people who don't know, the idea of combining two different species to create a more productive species, right? What generally are the other species that are used there?
So hybrid poplars really have their home as windbreaks and shelter belts.
Right. They're not something we're planting on the natural land base.
They are not currently allowed to be planted on crown land because they are considered exotics. Right. So, yes, so you can put anything you want, though, on private land.
Right, it's private land, yeah.
And the program in Saskatchewan at the old Indian Head Shelter Belt Center that was recently sold, sadly, was over 100 years of production of shelter belt material to farmers across the whole prairies. Okay. And a lot of those original clones, as we call them, because it's an individual that then gets propagated multiple times. Okay. Those were actually brought over from with immigrants from Eastern Europe.
Oh, okay. So it's Populus tremula and some other stuff?
Yeah. So there's two main groups of poplars that we deal with here. One are the aspens. Right. So that's Populus tremuloides. Yep. And that's the one we see out in our boreal forest that grows on its own, or
trembling aspen,
or with spruce. Right. Yeah, trembling aspen's got those lovely trembling leaves.
Yeah, nice white bark, and yeah.
Yeah, and then there's the balsam poplar, right? And it grows along the river valleys mostly, and it's more of a riparian species, so it likes the waterways. Mm-hmm. And then in southern Alberta, we have cottonwood, right. Which is Populus deltoides.
Right, that's eastern cottonwood, right?
No, we have a western cottonwood. There is an eastern cottonwood as well. Right. So it's also a deltoides. Right. So the balsam poplar and the aspens do not breed naturally. Okay. With each other. Right. But the deltoides, cottonwood in the south, and the balsam, they have a whole intergression zone where they intermix.
Okay.
And they do hybridize naturally. And
Okay.
they are hybrids, but that occurs naturally. Plus, you could do it artificially.
Right. Okay.
So those are some of the species. Then there are other species on the coast. There's Populus trichocarpa, black cottonwood, which is very similar to our balsam poplar.
Okay.
And a lot of breeding was done between trichocarpa and deltoides that was really initiated a lot of the hybrid poplar work in North America.
Oh, okay. For some reason, I had this assumption that it was like European poplar and something else over here, right? I don't know why.
Yeah. So some of those original clones that I talked about that came over, they were European.
Yeah.
And they have quite a complicated parental background. So,
okay.
So there's one in the poplar world, a cross between two species can often be given a name of its own.
Oh, okay.
Which
right, that makes sense.
It's confusing, but it gets a name of its own.
I imagine trying to identify it on the spot is probably a pain in the ass.
Yeah, you go, well, it's got this characteristic and that characteristic.
Yeah.
But there's two species, Laurifolia, Populus laurifolia, and Populus nigra.
Oh, okay. Right.
So that particular cross type was made a lot at one time or occurred naturally.
Right.
And it has a name, 3 different names. It's called Berlinensis, Ramusciana, and Petrosciana.
Okay.
Which gives you an idea of where it came from in the world. The sound of those names.
Yeah.
And that name actually identifies that hybrid type.
Okay.
So some of those actually then were bred with our native deltoides here.
Oh, okay.
So poplars are males or females.
Yeah.
They don't have both on the same tree.
Mm-hmm.
And so you have a female. So we have a female deltoides, and it gets crossed with a male Petrosciana. We then have a really complicated cross there in terms of the progeny.
All right.
So those crosses will be made. You can make them. It's quite an elegant system. You can actually take branches with the sex buds on them, flower them in the greenhouse, collect pollen, then bring females in, flower them in the greenhouse, and do your cross in the greenhouse and get the seed within 6 weeks or so.
That's awesome. It's viable seed, and yeah, that's cool.
And then you can grow your seedlings. So you grow, really, you grow 10,000, let's say.
Right.
And then you pick. This is the beauty of poplars.
Yeah.
Why I love them so much. You could screen tons of progeny, and lots of them are terrible.
Right.
They're not good.
Yeah.
And then you have some that are just like the parents. But what you're looking for is hybrid vigor, which is exactly what we look for in rice breeding and corn breeding. You're looking for individuals that are better than the parents.
Right.
Way better than the parents.
How anomalous is that?
So if we were to test 10,000 progeny, we might pick 20 or 30 to continue to test more.
It's very selective.
Out of there. Very selective. And so you've now picked the best of the best out of that population. Extreme, really. And they'll be super fast growing. You can screen them for the disease that is your problem in your area, whether it's a rust or a canker or whatever.
Yeah.
And then with these poplars, because the beauty of these poplars is you can take cuttings from them and root the cutting.
Okay.
To propagate more of that individual. And that's how all the shelter belts were produced.
Right. So straight up just take a cutting of it, stuff it in the ground, let it grow.
Yep.
Yeah. Isn't that crazy?
It's crazy.
It's crazy that trees are that resilient, especially poplars, right? Like they're a fascinating species. Like I don't think people understand when they're driving in the fall and they see there's a circular patch of aspen trees they all still have their leaves and nothing else does. And they're like, well, why does that? Like, what's specific about that environment? They're not realizing, no, that's one organism. That's one cohort, right? It's you can actually have 100 trees and they're actually the same exact tree, just connected
same
underground.
Genetics, basically, yeah.
Yeah, it's interesting. It's just,
So the aspen you can't do that with, though.
Okay.
Only the poplars.
So it's not tremuloides. It's only the poplars.
Tremuloides is a bit trickier to work with. You have to go to either tissue culture or some kind of root suckering.
Could you do
protocol.
tremuloides with tremula?
Yes, so that's where the hybridizing on the aspen side occurs. It's between tremuloides and tremula, the European aspen, or Davidiana, which is the Asian aspen.
Okay.
And they were actually all thought to have originated from the same species within the aspen group. It's a much simpler, less complicated classification within populace, within poplars.
And so you can take. So which ones are the ones that we would use for like say to shorten rotation times to like 30, 40 years for like a pulp mill on a private landscape or something, right?
So here you could go to 20 years.
20 years.
Yeah.
That's crazy.
Yeah, it's great. So those, well, when I was working up with Alberta Pacific running their research program for the poplar farms, we were working with both poplars and with aspens.
Oh, okay.
And so we had crosses where we used our native balsam as well as one of the parents in those programs. And then we used our native tremuloides as well. And then I had pollen from Europe, and we had some Davidiana. Actually, they're called landrace trials, where you bring a population from another area and you establish it and then have that as a parent material to use in the future for breeding. Okay. For hybrid programs.
Yeah. It's interesting. So so just to be clear, that's all being done on private land. Yeah. So,
absolutely. So all private land, farmers would sign up for the program in that case and work with the company to establish those stands. So
I think some people get afraid when they think about you creating this super productive, fast growing crop that's going to take over the forest or something, right? But that's not allowed to happen. So
these poplars, it is interesting because they are extremely intolerant. So you know what that means in the forestry world. They don't like competition. They like to have lots of light. They want a perfect site. I mean, these things are babies.
Right.
They need to be babied to get the most out of them. If you planted them out in the regular forest, they would never make it.
Interesting. I didn't know that.
They're not going to make it because it's too much competition. There's too many neighbors too close to them.
So they're very delicate species, but
they want, these hybrids that to get the most out. I mean, look at a shelter belt around a farm.
Right. It's
got lots of light, lots of nutrients, no doubt. It's got no competition. They're well maintained.
Yeah.
They're beautiful.
Right.
You know, they provide an incredible service. They provide phytoremediation services. They block sound. They block odor, wind. Yeah. They protect that farmhouse.
All that stuff. Yeah.
They do all kinds of great things, and there's a huge role for them.
So are most of the shelter belts that we see in Alberta, are those mostly hybrids? Or
they're all hybrids.
They all are hybrids.
Well, okay, maybe not 100%.
Right.
Yes, they're all hybrids.
I remember looking at them when I was younger, thinking like, okay, so those are cottonwoods, and like I don't personally know if I actually know the difference between like a cottonwood or the hybrid, right? So like they're mostly hybrids. That's interesting.
Most of them have cottonwood as part of the parentage.
That's what I mean. Like they look like a cottonwood to me.
Yeah.
But then whether or not they're hybridized with something else, I would have no idea. So it's definitely you need to be specialized to see the difference there because there's such minute details, I imagine.
And typically people want males as well.
Okay.
Because the females produce the catkins in the spring.
Right.
And then there's that fluff that everybody talks about.
Yeah.
And the fluff kind of jams up everything. It looks like it's snowing out there.
Yeah, exactly.
And that's just the seed blowing around. It's not actually, I think there's also a lot of people think they're allergic to that, but really mostly they're probably allergic to the pollen when it flows earlier in the season.
Right.
But this is just a seed, it's a little, piece of tissue that's attached to that seed to blow it around.
Right.
It's not typically thought to be an allergen.
Right. That makes sense. We're coming up on an hour here already. See, told you it goes fast.
It does. Get me talking about things I like.
Yeah, exactly. That's the whole point of this, right? So one thing that came up in the emails between you, myself, and Ellen, she pointed you out as she said we could talk about frankenforests. I don't know.
That's nice.
I don't know what the hell frankenforest is. So clue me in. What's going on there? What's that all about?
Well, it's not my term.
Okay.
So to define her term of a frankenforest, but my guess is what she's getting at is identifying the misconception that often happens when people hear the word genetics.
Right.
They then think of a genetically modified organism.
Right.
And genetically modified organisms, which is what's gone on for many years in agriculture.
Hot topic right now.
Roundup Ready canola, for example, is a genetically modified or a GMO.
Or corn. Like people don't realize that corn was the size of wheat, and now it's a grass. It's literally a wheat or whatever. Watermelon. Seedless watermelons don't exist, or bananas, right? Or all that stuff, right? Like everything you buy in the grocery store is genetically modified, selectively bred. Yeah.
Okay, so you've put two things together there that are not equal.
Right. Okay.
You put genetically modified and selectively bred.
Right.
So genetically modified usually means that it's been some kind of gene modification in a petri dish.
Really? Okay, I didn't realize that was the actual definition.
And well, there are several definitions, so please don't quote me, but you can look up GMO. It's got an official term in the federal government has an official term.
I assumed that GMO meant things that were also just selectively bred. Okay, but it doesn't.
Absolutely not.
Oh, okay. Interesting.
Absolutely not. So a GMO is an insertion of genes from another organism, typically very distant.
Okay.
Sometimes maybe parallel in some way or fashion, and that is inserted using a vector of some type.
Okay.
Into the genome of an individual you want to modify.
Right. Okay. I didn't realize they were different. Yep.
Selectively bred is basically doing Mother Nature in a greenhouse or in a seed orchard, where you're painting pollen or blowing pollen onto the female conelet or flower. And in essence, you're just trying to, that's the way classic agriculture has been done. Right. So a lot of those advances actually in corn and things were done with very classic breeding approaches as well. Right.
They're selective breeding.
Where you get that modification component, for example, is with, say herbicide is the classic one.
Right.
With Roundup.
Okay.
And so inserting that gene for herbicide resistance into, canola, that is a genetically modified organism.
Okay.
Yeah.
So specifically selected for and inputted into something. Okay.
Yeah, or taking, I don't know, spider silk mechanisms and inserting that into a pig. And getting the pig to produce silk. That's
Spider
a
pig.
GMO. That's a GMO, right?
That's a movie I'd see. Spider pig sounds like a good one.
There's other new techniques coming out called CRISPR, where they're actually going in and doing gene editing.
CRISPR is fascinating.
Yeah. So again, I'm not a molecular expert, but as I understand it, they can go into that genome and pull stuff out.
Yeah.
So it's got huge potential in medicine.
Yeah, it's my understanding was that it's almost a cut and paste. They can just cut out the piece they don't like, put in the piece they do like, and call
or
it
not
good.
Put anything in, just pull something out.
Right.
So with the original work that was done on GMOs, and I think still happens quite a bit, when that insertion of that other genome or sequence of genome goes into another organism's DNA,
right,
they don't know where it goes. Exactly.
Yeah.
It goes in somewhere. And so they might repeat that over and over and over.
Right.
And then test those individuals to see how stable the expression is of that modification. And that takes a long time, and it takes a lot of testing to make sure that you have a stable expression of that genome, that modified genome.
Right.
And so there's a lot goes into anything agriculture. For example, obviously, before any of those seeds go out.
Right. Yeah. So we're not doing any, as you pointed out, genetic modification on tree species. Then we're doing just selective breeding.
We're doing selective breeding. What we're doing is we're using the genome to help us identify and link to that phenotype that we're after more quickly.
Gotcha.
And speed that process up.
Right. So the Frankenforest thing was just it's a fancy term. It sounds good though. It sounds intriguing. Like Frankenforest, what could that possibly mean? So the whole idea of that is she was referring to just the idea of having a GMO species on the landscape, and that's not what's happening. So
it is not what's happening. No, and in fact, if you go to the Alberta Forest Genetic Resources Council website, you will see that there is a statement there which says that GMOs are not allowed on Crown land in Alberta. And all of that is regulated through the feds. And so there's a whole series of testing you have to do to get approval for even the testing in a confined area before anyone ever would get to an unconfined testing. And no one's ever gone to an unconfined testing for a tree species, as far as I know, in Canada.
Okay. Interesting. Awesome. You got any final thoughts regarding this? I mean, I think we've covered a lot of stuff, and I mean, I'm sure we could get more in depth into. Like CRISPR is one that I wasn't sure if we could bring it up or not. I didn't think that you were working with that, but CRISPR blows my mind.
I'm not working with it.
Yeah, so CRISPR blows my mind. They're doing all kinds of crazy stuff. They can select for the Alzheimer's gene, but they don't. I guess the problem that they're having with it now is, although they can do these works, they don't exactly know the ramifications of what they're doing yet. So they're still figuring that out. They don't know for sure that, like, if you pull the Alzheimer's gene out that you might be shortening somebody's legs or something. Like, I don't know. It's
no, there's a lot of interactions that go on in, between our chromosomes and with genes on those chromosomes. And I don't think we fully appreciate all of that.
Yeah, I don't think we can understand the math behind it, let alone try and understand what the ramifications are of it. Yeah.
And then put those people in different environments too.
Yeah.
But on the plant side, there's a lot of work being done in that, in the CRISPR area with poplars at the Umeå Plant Sciences Center in northern Sweden. They're very cutting edge in all of that kind of research. It's quite exciting.
That's cool.
Yeah, they're very top-rate scientists over there working in that area.
That's cool. What would you say that was called?
The Umeå Plant Sciences Center.
Umeå.
Yeah.
Cool. I'll check that out. Do you have any final thoughts regarding forest genetics? Maybe something that people might want to know, an interesting factoid, or we can just wrap this whole thing up, tie it in a bow, and send it off.
Well, I just think that, genetics plays a role in our lives, throughout our lives, all aspects of it. And I think sometimes people are really scared by the G word.
Yeah.
When I was a grad student, it was like, oh, she's working on the G word.
Yeah. Oh, for sure. Yeah.
And so it's not scary. And it is really important to understand, I think, at least on some level, the opportunity that, that we can take advantage of, whether it's agriculture or forestry. And, genetics is our friend. And it shouldn't be shelved over there. It needs to be integrated in our forestry communities. It really needs to be integrated into our silviculture mainstream thinking. It is simply one more tool in the toolbox that the silviculture forester has. Yeah. Whether it's fertilizer, thinning, a site prep, using the right genetic material and the right seed lots and understanding the importance of that, I think is critical to our forests of the future in this province. Absolutely.
And not just for productivity, just for the resilience towards pests and drought and all of these kinds of things. So, it only makes sense that if there's human-caused climate change, so something that the forest hasn't come into contact with, that humans might have to give the forest a bump, help them out a little bit, get them, get them pointed in the right direction, right? Yeah. Yeah, so no, it makes sense to me. Perfect. I remember it ties into, I remember I read a Margaret Atwood book when I was younger, Oryx and Crake, and it was this dystopian. Yeah, I don't know if you've read that book, but it's a dystopian future about, we went haywire with genetic engineering, right? And we've got pig horses and people monkeys and all this crazy stuff. And it's just
unicorns?
All kinds of crazy things that, like monsters and stuff, right? And I don't think that's the direction we're headed in, but there's a lot of legality and a lot of research being done to make sure that we're not putting ourselves in a dangerous situation. So
no, I think we can really help our forests move forward, and I'm in this game because I think it can make a difference. Yeah. And it's not all just lab bench work. It's applied. It's going to help us with our forests, and I'm pretty excited about seeing the outcomes from our current study. Yeah, me too. No, I'm looking forward to maybe we'll have it back on when you guys have wrapped things up. Sure, sounds good. Yeah. Thanks for having me.
Yeah, thanks a lot for coming on. Thanks a lot for listening, guys. If anybody has any questions, they can reach out to me on Twitter, Your Forest Podcast. There's no vowels in podcast on that handle, I think. I suck at Twitter, though, so better off to use Facebook. I have a Facebook page, as well as Instagram, if anyone wants to follow. LinkedIn is just my name, Matthew Christoph. Yeah, check that out. You can send me an email at yourforestpodcast@gmail.com, and I'll get back to you as soon as I can. Absolutely. I like to get those people inquiring about the podcast and asking questions so I can send them out and find the right answers. So I haven't had any specific inquiries about actual questions yet regarding content, but people are asking about platforms that I'm on. I guess I could say that now. We're on iTunes, the podcast website, yourforestpodcast.com, and Stitcher, and I'm actually on Google Play now too. So Spotify's tough. I haven't been able to get on Spotify. They're very selective. I'll see what I can do. If anybody wants any other platforms, I'll shoot me an email and I'll throw it up on there. So anyways, thanks a lot for listening, guys. If you're on iTunes or Stitcher, you can go ahead and rate and review the podcast. I really, really appreciate it. It helps me out a ton. Thanks a lot, guys. Thanks for listening, and we will catch you next time.